Hello, welcome to this lesson on relations. This is ITE 1812 Mathematics for IT. Let's first look at the learning outcomes. So by the end of this lesson, you should be able to define a relation, an inverse relation, and a composition of relations. And find the inverse of relation and composition of relations. And identify and describe the properties of relations. And also identify equivalence of relations, compute equivalence of classes, and find the closure of a given relation. So firstly, the introduction. So we find in many naturally occurring phenomena, we find that two variables may be related with some kind of relationship. So in this lesson, what we are going to do is to mathematically describe and represent this kind of relation. So here on this table 9.1, you have a relationship between time spent and the marks obtained for a certain subject. So there can be variable number of hours, 3 hours and 60 marks, 2 hours and 80 marks, and so on. So each data point from the above table may be represented or can be called as an ordered pair. So in this case, the first value represents the study time and the second value represents the marks. So in this example. So now we have several or a set of ordered pairs, 360, 280, 155, and so on. So for this example. So this set of ordered pairs define a relationship between study time and marks. So any set of ordered pairs x and y is called a relation in x and y. So going on further, the set of first components in the ordered pairs, they are called the domain of the relationship. And the set of second components in the ordered pairs is called the range of the relation. So identify the terminology here, the domain and the range. So usually the symbol used for a relationship is capital R. It denotes a relation. And negation, you can also represent negation of a relationship or a relation by the stroked out R symbol, crossed out R symbol. So for instance, the ordered pair 360, which belongs to the real number set, we can then say, so this is how we put it. This is the terminology. 3 is R related to 60, and it is written as 3R60. So you might see these kind of notations when you deal with. Now we move on to the formal mathematical definition of a relation. So a binary relation R from set X to a set Y is a subset of the Cartesian product X product Y if X, Y in the relationship, we write X, R, Y and say that X is related to Y. If X is equal to Y, we call R a binary relation on X. So this is the formal mathematical definition of a relation. So we have two special remarks about relation. So a relation may consist of a finite or infinite number of ordered pairs. So that's number one. And then the X and Y components that constitute the ordered pairs in the relation, they do not need to be numerical. Right, take an example to better understand. So let's take X including 2, 3, and 4, Y having 3, 4, 5, 6, 7. We define relation R from X to Y, so that X and Y is the relationship if X divides Y. So you can find the elements of R, so the ordered pairs of R, 2, 4, 2, 6, 3, 3, 3, 6, and 4. So this is how you define a relationship. Another example, so let R be a relation on X where X includes 1, 2, 3, and 4, defined by X and Y in R. If X is smaller than or similar to Y. So X and Y also in X. So then we can define the relationship R as 1, 1, 1, 2, 1, 3, and so on. So this should satisfy the condition given in the relationship. Next, the definition of the inverse of a relation. So let R be a relation from X to Y. We can define the inverse of that relation denoted by R to the power minus 1 is the relation from Y to X given by R inverse YX, where X and Y is the relationship. Take an example once again to explain it better. So we can take the same example from before, and firstly, the original relation contains 2, 4, 2, 6, 3, 3, 3, 6, and 4, 4. So when you inverse it, you have the inverse relation 4, 2, 6, 2, 3, 3, 6, 3, and 4, 4. So basically what you do is here you interchange the values X and Y. So you get the inverse relationship or inverse relation in this example. Another definition, composition of relation. So what do we do when we have multiple relations? You can define composition relations. So let R1 be a relation from X to Y, and R2 be a relation from Y to Z. Then the composition of R1 and R2, which is denoted by R2 dot R1, would be the relation from X to Z, defined by R2 dot R1 XZ, where XY in R1 relation and YZ in R2 relation for some Y in Y. Right. So this is the mathematical definition for composition of relation. Going back to an example once again, so we have R1 and R2, where you can see the different elements, 1, 2, 1, 6, 2, 4, and so on for R1, and R2 has 2U, 4S, 4T, and so on. So you can define, in this case, the composition of R2 and R1, which includes, so when you have 1, 2, and 2U, it represents 1U in the composition relation. 1, 6, and 6T, for example, it denotes 1T. 2, 4, and 2U, or 2, 4, and 4T gives you 2T, and so on. So it defines the elements of the composition relation. A special remark about composition relations. Let R be a relation on the set X. So the powers are to the power n, where n is 1, 2, 3, and so on, is defined recursively. So this can be defined recursively by R1 is R, and R to the power n plus 1 is Rn dot R. Now we introduce 4 special properties of relations: reflexive, symmetric, transitive, and antisymmetric. So first take a reflexive property. So how is it defined? So if X is in the relationship R for all X, we call that relation as a reflexive relation. And then symmetric property holds if whenever XY in the relationship R, then YX should also be in the relationship R for all X and Y in X. So that's number 2. And number 3 is transitive property, is whenever if X and Y in the relationship R and Y and Z in the relationship R, then X and Z also in R for all X, Y, and Z in X. So that is transitive. So the fourth one is antisymmetric. A relation R on a set X would be antisymmetric if for all X and Y in X, if XY in the relationship R and YX in the relationship R, and then X is equal to Y. So we will look at an example to better explain these four properties. So here, consider these 6 relations from R1 to R6. So you can discuss the reflexive, symmetric, transitive, and antisymmetric properties of the above relations. So if you take reflexive, and if you take R3 relation, for example, so it has 1, 1, 2, 2, and 3, 3, and also 4, 4. So if you refer back, it has to have X, X in the relationship for all X. So X is here in this case 1, 2, 3, and 4. So we are referring to R3, where it has X, X. That means 1, 1, 2, 2, 3, 3, and 4, 4 for all X. So that satisfies the condition for us to call this a reflexive relation. So for example, R3 is a reflexive relation, and also if you examine in the similar way, R5 is also reflexive. And then symmetric. So what do we mean by symmetric? If you go back, so whenever X and Y is in the relation, if then Y and YX should also be in the relation for all X and Y. So let's take, for example, R2. So you have X and Y to be 1 and 2. And you see that in R2, you have 1, 2, as well as 2, 1. So you will see that it satisfies the condition to be called a symmetric relation. So R2, because it contains 1, 2, and 2, 1, we can call that it is a symmetric relation. Similarly, if you examine R3, you would see that it also satisfied the condition to be called a symmetric relation. And the next one is transitive. So transitive is if whenever X and XY in R and YZ in R, then XZ should also be in R for all XY, Z. So now if you take a look at this example, so if you look at R4, R5, and R6, you will see that it satisfies the condition to be a transitive relation. So we go back for the last one, which is antisymmetric. So it is when if for all X and Y in X, if XY in the relationship R and YX also in the relationship R, then X should be equal to Y. So this condition is satisfied by R4, R5, and R6. So if you go into the individual elements or ordered pairs, you will see that these conditions are met in the mentioned relations. So that's how you arrive, or that's how you decide these properties, reflexive, symmetric, antisymmetric, and transitive properties of relation. Right, so we move on to another concept which we call equivalence relations. So this is a relation that is reflexive, symmetric, and transitive on a set X. So if all these conditions are met, we can call that an equivalence relation on X. We look at an example to understand the equivalence relations. So consider the relation R where you have these ordered pairs on 1, 2, 3, 4, and 5. So we are required to show that R is an equivalence relation on 1, 2, 3, 4, and 5. So let's see how to approach this. So you need to see whether the relation is reflexive, symmetric, and transitive on a set X. So set X is in this case 1, 2, 3, 4, 5. And you need to consider these properties separately to check whether this is a equivalence relation. So you take one by one. The relation is reflexive because 1, 1, you have 1, 1, 1, 2, 2, 2, 3, 3, 4, 4, and 5, 5 in R. And so the reflexive property is fulfilled. And then the symmetric property, it is symmetric because whenever x, y is in R, yx is also in R. So that's how we check whether the symmetric property is satisfied. And then also transitive, because whenever xy and yx are in R, xz is also in R. So that's how to fulfill the transitive property. So since R is reflexive, symmetric, and transitive, so we can call R is a equivalence relation on 1, 2, 3, 4, 5 on this set. Right. So that's how we decide whether it's an equivalence relation. So the general idea behind equivalence relation is that is a classification of objects which are in a way alike. Right? So that's the idea of doing that. So the two elements x and y that are related by an equivalence relation are called equivalent. So notation x equivalent y is often used to denote that x and y equivalent elements with respect to a particular equivalence relation. So this is how we break down the concept of equivalence relation. Another important definition, partial orders. So a relation R on a set X, we call it a partial order if R is reflexive, antisymmetric, and transitive. So similarly, if you, if you take an example, a relation, you need to check whether the relation is reflexive, antisymmetric, and transitive to see whether it can be defined as a partial order. And then the concept of equivalence classes. So this is the formal definition for that. So let R be an equivalence relation on a set X. So for each element A in X, the sets A defined as set A in X in X, X are related to A, are called the equivalence classes of X given by the relation R. So let's take an example to describe this. So find the equivalence classes for the equivalence relation. So you are given an equivalence relationship and you are required to find the equivalence classes on this set 1, 2, 3, 4, 5. So let's see how we do this. So in the previous example, we have shown that the relationship R is an equivalence relation on 1, 2, 3, 4, 5, that set, right? So the equivalence class 1 containing 1 consists of all x such that x1 is in R. Therefore, 1 is 1, 3, and 5. So similarly, you can find the remaining equivalence classes. For 2 and 4, you have 2 and 4. For 3, and 5 equivalence classes, you have 1, 3, and 5. So therefore, there are 2 equivalence classes we can identify. There are 2, 4, which includes 2 and 4, and then 1, 3, and 5, which includes 1, 3, and 5. So this is how you arrive at the equivalence classes. Right. So we move on to the next important property, which we denote as the closure properties. So let's try to understand what is meant by closure properties. So let's consider a given set X and the collection of all relations on X. So let P be a property of such relations, such as being symmetric or being transitive. So we have so far identified several properties on such relations: symmetric, transitive, antisymmetric, and reflexive. So yeah. So let's say a relation with property P will be called P relation. The P closure of an arbitrary relation R on X, written as PR, is a P relation such that R is a subset of PR, which is a subset of S. Okay. So for every P relation, S containing R. So we will write reflexive R, symmetric R, transitive R for the reflexive, for the corresponding property. For the reflexive, symmetric, and transitive closures of R. So generally speaking, PR need not exist always, but there are conditions. However, there's a general situation where PR will always exist. Suppose P is a property such that there's at least one P relation containing R, and then the intersection of any P relations is again a P relation. So this is written as PR is equal to intersection of S. S is a P relation and R is a subset of S. So thus, one can obtain PR as the intersection of relations. However, one usually wants to find PR by adjoining elements to R to obtain PR. So depends on the different relations and properties you need to incorporate. And now going into specific closures, reflexive and symmetric closures. So we introduce a theorem which tells us how to obtain easily the reflexive and symmetric closures of a relation. So what does this theorem tell us? So let R be a relation on set X, then R union delta X is the reflective closure of R, and number 2, R union R inverse is the symmetric closure of R. So here, what you mean by delta X is XX. If you remember about reflexive property, you will remember that XX condition has to be met by the relation so that it can be called a reflexive relation. So delta X denotes XX in this case. So it's the diagonal or equality relation on X. So this is how you define, or this theorem tells us how to define the reflexive and symmetric closures of a relation. So in other words, reflexive R is obtained by simply adding to R those elements XX in the diagonal which do not already belong to R. And symmetric R is obtained by similarly adding to R all pairs of Y and X whenever X and Y belongs to R. XY belongs to R. So that's how you fulfill the conditions for reflexive or symmetric closures. So here's an example. Find the reflexive closure and the symmetric closure of the relation. So we are given a relation R, which includes the ordered pairs 1, 1, 1, 3, 2, 4, 3, 1, 3, 3, 4, 3. So on the set X 1, 2, 3, 4. Right? So you need to find the reflexive closure and the symmetric closure. So to find that, you need to fulfill the condition. So the reflexive closure is closure of R is reflexive R, which should be the union of R and this specific set 2, 2 and 4, 4, which is equal to 1, 1, 1, 3. And you basically need to include those missing ordered pairs. And similarly, the symmetric closure of R is symmetric R, which has to be obtained by R union 4, 2 and 3, 4. So that it fulfills the condition for a symmetric closure. And eventually you find that, arrive at the symmetric closures, or in the case of reflexive, you arrive at the reflexive closure. And then another concept we identify as transitive closure. So the transitive property, of course. So let R be a relation on a set X. We define R star to be the union of all the R to the power I. Right. So there's a theorem connected to this. So let R star is the transitive closure of R. Suppose X is a finite set with n elements. Then you can define R star to be R union R to the power 2 union R to the power 3 and so on until R to the power n. So this is the theorem on transitive closure. And finally, you arrive at this relation from the theorem. So let R be a relation on set X with n elements that then to get the transitive R, you have to have R union R to the power 2, R to the power 3 until R to the power n. So that's how we arrive at the transitive closure. So going again to an example, so find the transitive closure of the relation R. R is given as 1, 2, 2, 3, and 3, 3 on X 1, 2, and 3. So how do we arrive at the solution? So the transitive closure of the relation R, since X has 3 elements, 1, 2, and 3, should be obtained by taking the union of R with R squared, R to the power 2, that is R dot R, and R to the power 3, R to the power 2 dot R. So noting that these relationships R to the power 2, that is R dot R, is 1, 3, 2, 3, and 3, 3, and R to the power 3, that is R to the power 2 dot R, 1, 3, 2, 3, and 3, 3. Hence, you get the transitive R by taking the union of all three relations, R to the power 2, and R to the power 3. So this is how you get the transitive closure of a relation. And then this concept of n-ary relations. So the relationships are among elements from more than 2 sets. They are defined using n-ary relations. So far we have been discussing about 2 elements or 2 sets. But if you go for multiple, then you have to consider n-ary relations. So by an n-ary relation, we mean a set of ordered n tuples for any set X. A subset of the product set Xn is called an n-ary relation on X. So in particular, a subset of X to the power 3 is called a ternary, and so on. So we can go even further in terms of n-ary relations. So a definition on n-ary relations. So let X1, X2 until Xn, they are all sets. So an n-ary relation on these sets is a subset of all the product in among X1, x2 and until xn. So these sets x1 until xn, they are called domains of the relation, and n is called the degree. Right? So this is about the n-ary relation. So taking this example, so let R be the relation on n times n consisting of triplets x, y, and z. So where x, y, and z are integers with x less than y less than z, then 1, 2, and 3 they are related. They are related, but 2, 4, 3 they are not in R. So the degree of this relation is 3. Its domains are all equal to the set of natural numbers. So this is related to how you go about looking at n-ary relations. Right. So that brings us to the end of the lesson. So we discussed about relations in detail in this lesson. So in the next lesson, we will talk about Boolean algebraic axioms and the duality principle. So thank you and see you in another lesson.